Hi Chem students, let's talk about Le Chatelier's principle. We'll begin by remembering that reactions at equilibrium are very much like a seesaw where there's some sort of balance between the amount of reactants and products that we have. Sometimes that reactants and products ratio is fairly similar, so we'll get an equilibrium constant that's approximately 1. But sometimes that balance is struck when there's a lot more reactants. That's when K will be very, very small, less than 1, or when there's a whole lot of products, when K is very, very large. So that's where we get these terminology things like we say at equilibrium, if K is less than 1, the reactants are favored, or if K is much greater than 1, then the products are favored. So just some terminology there, but we have to keep in mind that it's much like a seesaw. And a seesaw, if we do something to the seesaw, it will go out of balance. And so will our equilibrium if you're to change the conditions in some way. Le Chatelier's principle essentially says that if we do make one of these changes, if we add a stress to the system, then the system is going to move to try to remove the stress. So if you push, it's going to push back. If you pull, it's going to pull back. Stresses that reactions can have are adding or removing reactants, adding or removing products, changing the volume, and even changing the temperature. These things will adjust the equilibrium, make it reestablish itself, and in the case of temperature, we'll do even more. And so we're going to have a separate video at some point about temperature. So let's look at this balance once again, just to get an idea of how Le Chatelier's principle plays out. So we've got this seesaw here with some books on it, and it's currently at equilibrium. So we would say that since it's at equilibrium, its Q, its reaction quotient, and its K are the same value. However, just remember that Q is a ratio of the products divided by the reactants. In this case, we have an equal amount at equilibrium. Well, what if I was to add to the product side 2 new books? Well, we certainly would see it tilt to the right like this. So what the system would do, since we're not at equilibrium anymore, and Q is now greater than K because the products, the numerator got larger, therefore Q got larger. If Q is greater than K, the reaction is going to shift back to the left. And you can see what's going to happen here is by sending one book over to the left, just one book over to the left, both sides will then be equal again, and we've reestablished equilibrium. That's what Le Chatelier's principle is. It's this response to the stress. The stress in this case, adding 2 books. The response, shifting to the left so that we get back to equilibrium. So our plan of action will always be like this. We're going to identify how the stress affects our reaction quotient. We're going to compare that to K. And as usual, let this decide which way we're going to move to reestablish equilibrium once again. For temperature changes, there's more stuff going on because the equilibrium constant will also change. So the difference here is that we're not only going to shift equilibrium, but we're also going to establish a new equilibrium at a new equilibrium constant. And so we're going to need to keep track of that when we play with temperature changes as well. For this video, it's just about concentration changes. So here's 2 examples to kind of give you the idea of how we would do real problems. Our reaction is this 2NO2 plus O2 goes to 2NO3. And initially, we're at equilibrium. That's what we always want to say. So what would happen if this system at equilibrium, what would happen to it if we added some NO2, if we increased the concentration of NO2, which is one of the reactants? So we're currently at equilibrium. So what we need to imagine is what would happen to this system? Well, the NO2 would get larger. So that would mean one of the pieces in the denominator would get larger. And we know that Q is equal to this expression at all times. Well, currently, we're no longer at equilibrium. We were at equilibrium up here, but now the denominator is larger, so Q has gotten smaller. That means Q is now less than K. If Q is less than K, then we now need to look at which direction this will move. So we've identified how Q and K are related. So here's this little graphic that I often use to remind myself how this all works. The equilibrium constant is some value, and Q can either be less than it or greater than it. If Q is less than K, we shift to the right. We always move towards equilibrium. If Q is greater than K, we shift to the left. We move towards equilibrium. Always write it exactly like this and draw your arrows towards equilibrium, and you'll never get one of these problems wrong. So in this particular case, we need to just focus on the Q is less than K, and we can see that the arrow is shifting to the right to get back to equilibrium. So that's what we would say. Our reaction is going to shift to the right to reestablish equilibrium. Let's try another example. What happens if the pressure, the partial pressure of the oxygen is decreased? Well, in this particular case, our Q sub P has is equal to our K sub P, and here's our equilibrium expression in terms of pressures. But what we're saying is, what would happen if the O2 pressure was decreased? So all of a sudden, this denominator is a little bit smaller. So if I take any number and I divide it by a smaller number, then my value is larger. So I end up with a larger Q than I had before. Then Q is increased, so that's now larger than K. We go back to our little graphic, and we realize that Q is greater than K, so we block out the Q is less than part, and we see that the arrow goes from the right to the left, so our equilibrium will shift to the left to reestablish equilibrium. To put that on a more numerical basis, since Q is greater than K, shifting to the left will make more reactants, making the denominator larger and decreasing the numerator, and that's how come it ends up equaling K in the end. So here's just a couple examples and an introduction to Le Chatelier's principle. We'll be doing more of this in class next time we meet.